Hello guys, very welcome back. In this video we'll be starting with the third important portion of the structural geology, which is in the part of the UPSC geology optional, stress and strain ellipsoid, stress strain relationship of elastic plastic viscous material. So now we'll be focusing upon the first word, that is stress. Let's start. So first in this we'll define what is stress, then we'll see what is the stress at a point, finally we'll see what is the stress on a plane, right, and finally we'll also see hydrostatic and deviatoric stress, right. So all structures formed when they were under the action of the given force, right. Now they will assume different features based on the properties of rock, that is the strength and the force and the inherent property of the rock, right. So if you see what is stress, stress is the force applied per unit area, right? So if we'll see its application point of view, the reason why the things which are made to pierce is so tipped and so pointed at the end is because when its area is decreased, the applied stress on the body, on the applied body, is very high, right, and hence stress, which we earlier defined force upon area, his unit is force, that is mass into acceleration, Newton upon L square, that is meter square, right, so, which is Pascal. The SI unit is Pascal, and 1 bar equals to 10 to the 5 Pascal, right. A very important point to discuss here is that always different forces are equated, never stresses are equated, right? Okay, so the denotation of stress is standard, that is sigma, right? And as per the definition limit, when delta A tends to 0, the stress is defined as it is shown here, right? Now, a force acting on a body can be resolved into normal stress and the shear stress. Suppose here is a body and the force is acting, right, this. Now, if we see what is the stress acting on this surface, the stress can be resolved into two parts. One is the normal stress perpendicular to the body, and other is the shear stress, right? Shear stress is also represented by tau, and normal stress is represented by the sigma, right? Next, we move to what is stress at a point, right? The first and foremost things for assumption is that the sigma fx, right, equals to 0, sigma fy equals 0, sigma fz equals 0. That is, the body must be stationary, okay? That is the first condition. Now, for an arbitrary chosen axis, right, we'll see here, suppose there is a body here, and as I've already told, it is stable. Now sigma zz will be limit delta A tends to 0 fz upon delta A, sigma zz is the normal stress. Now let's discuss what is sigma zz. First, z shows the face, right? So here the face, the first index refers to the plane in which the force acts, right? The plane, the face, right? So if you see here, so this is zy, and the face, so zy, the perpendicular is the x face, zx, the perpendicular is the y face, and if you see the xy, so this is the z plane, right? So this plane is z plane, okay? This and below that, these both are z planes, okay? So the first index refers to the plane in which the force acts. The second index refers to the direction of the resistive force, okay? So a resistive force, when sigma is applied, stress is applied like this in this direction, the component of the sigma perpendicular to this face is sigma zz is known as the normal stress. The component of sigma parallel to the Z plane is known as the shear stress, right? Okay, so all this. Now, since stress is a tensorial quantity, that is, it requires magnitude, direction, and the plane, right? So we represent stress tensor sigma ij as sigma x. Sigma x is here, right? Then tau xy, and then tau xz. So this is all the sigma, all the stress acting on the x plane. Okay, then these are all the y plane, and these are all the stresses acting on the z plane. The thing is, in order for the body to be rotationally equilibrium, in order for the body to be translationally equal, force in this direction on the body must be equal to the force in this direction, right? That is, tau zx and tau yx must be equal and must be opposites, must be cancelling each other, else the body will start rotating and we won't be able to calculate the stress, because stress, we are considering only the static bodies, right? So tau xy has to be equal to tau yx. So we can replace all these things, and this static body hence need only 3 normal stress and 3 shear stress. Hence, for arbitrarily chosen set of orthogonal axes xyz, 6 independent and only 6 independent quantities are necessary to specify completely the states of stress at a point, right? Which are these. Now, rather than using arbitrary axis xyz, it is convenient to choose new axis abc such that the shear stress is 0. Okay, tau AB, tau BC, and tau CA is 0. We can choose those axes, and this happens when the body is put in under the water, right? The 3 mutually perpendicular planes on which the shear stress is 0 are called the principal stress planes. Okay, the normal stress along these planes are called the principal stress axis. Okay, this A, B, C, this mutually perpendicular plane on which the shear stress is 0 are called the principal stress planes, and the axes is known as the principal stress axis. Suppose there is a cylinder and sigma is applied there. The stress would be the stress tensor sigma ij would be represented only by sigma, and rest all will be 0 because there is no sigma in the y direction or the z direction, and then this is 0. Similarly, the tau shear stress is also 0, right? Now, suppose there is a body on which only the principal, the stress, the normal stress are acting, and hence its representation would be sigma for the x, sigma for the y, and sigma for the z, right? And since the shear stress is 0, this orientation, the plane in which the body is kept, is known as principal stress plane, and these axes ABC are known as the principal stress axis, right? The second, the stress as a point, has been discussed. Now let's move to the stress on a plane. Again, we'll be starting with the very same start we started with the stress at a point. Suppose there is a body which is rotationally and translationally at equilibrium, right? Sigma 1 and sigma 3 is acting in such a way that the system is static, right? So here is sigma 1 which is acting, and this is sigma 3. As I already told, these are 0. Now, if we want to place a plane in this box and find out what is the stress acting on this plane, we will have to consider sigma 1 and sigma 3 as shown in the diagram, right? suppose the plane AB makes an angle theta with sigma 1, right? Suppose plane AB makes an angle theta with sigma 1, and suppose sigma 1, sigma 3 are the two stress acting on the plane. Now since stress can't be operated, right, stress is not able to operate, the focus should be put on the forces, right? Now the force by sigma 1 would be sigma 1 into OB, right, which is sigma 1 into AB sine theta if AB equals to unit. Then force by sigma 1 equals to sigma 1 sine theta. The force by sigma 3 would be sigma 3 into OA, which is sigma 3 into AB cos theta. If AB equals to unit, force by sigma 3 equals to sigma 3 cos theta. Now sigma equals to sigma 3 cos square theta plus sigma 1 sine square theta, right? The total force sigma equals to sigma 3 cos square. How? This is sigma. We have found by force by sigma 1 equals to sigma 3 cos theta, and force by sigma 1 is sigma 1 sine theta. So the total normal force would be sigma 3 cos square theta and sigma 1 sine square theta added would be total sigma, and the tau would be sigma 3 cos theta sine theta and sigma 1 sine theta cos theta as it is written. Since these are in opposite direction, there would be negative sign. Now we will transform this sigma 3 equals to 1 plus cos 2 theta by 2 what as sigma cos square theta, and sine square theta 1 minus cos 2 theta by 2. Finding out, we'll find that the normal stress is sigma 1 plus sigma 3 by 2 plus sigma 3 minus sigma 1 by 2 cos 2 theta, function of cos 2 theta, and tau is cos sine theta cos theta as 1 sigma 3 minus sigma 1. Sine theta can be written as sine theta cos theta has been written as sine 2 theta by 2. So normal stress, the normal stress on the plane is maximum when theta is 0, right? When the shear stress is maximum when sine 2 theta is maximum. Sine 2 theta is maximum when sine value of 2 theta is 90 degree, because sine 90 is 1. So 2 theta is 90 when theta is 45, right? So theta, shear stress on this plane, is maximum when theta equals to 45, right? So the angle would be 45 in order to make maximum shear stress. And hence, if you want to make a plank and you want that the cars need to face maximum stress or maximum shear stress, so maximum friction, right? So you need to have this plank at the angle of 45 degree, right? And finally we move to hydrostatic and deviatoric stress, right? Now when the principal stress are unequal on a body, now for our convenience, mean principal stress is computed, right? Hydrostatic and deviatoric stresses, when the principal stresses are unequal on a body, for our convenience, mean principal stress is computed. For example, this is the body and this sigma 1, sigma 2 and sigma 3 is 9, 5, 7 and 5. Sigma 1 is always the largest, sigma 2 is the middle and sigma 3 is the least among the forces, right? So for our convenience, the mean is computed as 9 plus 7 plus 5 divided by 3 equals to 7. So this is known as the hydrostatic stress, when the stress is equal in all the sides, right? This is known as hydrostatic stress, and the difference between 9 and 7, which is 2, right, is known as the deviatoric stress. Now very important concept is, if the body is a solid, hydrostatic stresses will never be changing the shape of the object. They will always be involved, or they may be involved would be a better word, in changing the size of the body but never the shape. The deviatoric stress is responsible for changing the shape, right? So these are known as the deviatoric stresses, and this is how they are represented, which I already discussed earlier. So we discussed 4 concepts. What is stress? Stress is force per unit area, right? The lesser the area, the more is the stress. Then we discussed what is stress at a point. Stress at a point can be described by a tensor quantity, a tensorial representation. This is how it is represented. And for a static body, only 6 components are needed to describe a body's stress, right? That is 3 normal stress and 3 shear stress, right? Then we discussed what is principal stress plane and principal stress axis, right? We discussed what is stress on a plane, and we got to a conclusion that the maximum shear stress is when the plane is at the angle of 45 degree, right? And finally, hydrostatic and deviatoric stress, where we saw the hydrostatic stress is responsible only for the size, and hydrostatic stress cannot change the shape, right? And deviatoric stress is responsible for the change of the shape, right? So that's all. Thank you.